everyone, this is Himabindu from the Department of CSIT. So today in this video I would like to explain about the concept called context-free languages and what are the problems involved in the construction of context-free languages and how to convert it to a context-free grammar we will discuss in this video. So coming to the introduction of context-free languages. So we already discussed about the what type of grammars and what type of languages we have in the theory of computation. So coming to the Chomsky hierarchy, we have the regular languages and it is a subset of context-free languages and which is a subset of context-sensitive language and which is a subset of unrestricted language or grammar. So these are all the different types of grammars or different types of languages we have in the theory of computation. So in this one, we are discussing about the context-free languages. So what is meant by this context-free languages and where it is located and how we are going to differentiate with the regular languages we will discuss. So what is meant by context-free language? It is a language which is generated by the context-free grammar or type 2 grammar. So here for every Chomsky hierarchy languages we have types of grammars. Coming to the RL, it is a type 3. So this is the type 3 grammar and it is a context-free language is a type 2 language. And this context sensitive is a type 1 and unrecursive or unrestricted grammar is a type 0 language, type 0 grammar. So these are all the different types of grammars. In this one we are discussing about the context-free language. So this context-free language which is generated by the grammar called type 2. So type 2 grammar which is going to be generating the context-free language. So here this is according to the Chomsky hierarchy. So this is the Chomsky classification and get accepted by the pushdown automata. So here for every language we are going to generate or accept the mission called every language it is going to be accepting the one mission. So coming to the RL, so this is the type 2 grammar which is we are going to accept with the finite automata which is going to be generated with the finite automata. And from coming to the context-free language which is going to be generated by the pushdown automata, PDA, pushdown automata. So like this, we are going to describe the context-free language which is going to be generated by the type 2 grammar. So, and also it is going to be accepted by the pushdown automata. And coming to the closure properties. So closure properties of context-free language. So here when we have union operation. So union operation with the two languages we can perform the operation, union operation we can perform for the two context-free languages. And also we can perform the concatenation operation. So concatenation operation and clean closure. So clean closure, so is union, a dot and clean closure and reversal operation and homomorphism and inverse homomorphism and substitution and init and prefix operation. So and quotient and regular languages. So this is the subset of, so regular languages is a subset of context-free language so that we can perform the operations on regular languages also. That is one quotient with the regular language and cycle operation and union with the regular languages. So we can also combine the context-free language with the regular languages. So we can perform two operations, we can perform the operation in between the two languages also. That language is only for the regular languages. Why? Because the regular language is a subset of context-free language. And intersection with the regular language. So context-free language, intersection with the regular language and difference between the regular language. So CFL difference, context free languages. So these are all the closure properties we can perform on the context free languages. And context free language is not closed under some specific operations. So here not closed means, so previously we discussed about the closed operations. So now not closed means after doing that operation, so on the context free language, the resultant language not remains to be a context free language. So here previously what are the closure properties we discussed. So if you perform the operation between a CFL1 and union CFL2, so we will get a result as a context free language only. So result is going to be in the same language. But here if we consider the context free language which are not closed under some operations, the result of the two languages operation result is not a context free language. So that is, so here the closed operation, so not disclosed operations we can say that. So context free language, disclosed operations. So intersection and complement and subset and superset and infinite union and difference. So these are the all operations which are not having the result as a context free languages. So these are the disclosed properties. And deterministic property, coming to the determinism. So here we already discussed the word determinism and non-determinism in the finite automata. So non-deterministic in the sense we can have the state, one state it is having the multiple inputs or same inputs we can reach the multiple state. So while coming to the deterministic, it is only a particular thing. So particular thing in the sense, so if we have one input, we can map it to a only one state. So we can't map for the same input to the another state. So that is nothing but deterministic. So here this property is also one of the properties of context free language is deterministic. So deterministic property. So here we have the deterministic CFL and non-deterministic CFL. So coming to the, till now we discussed about the finite automata. We will discuss about the context free language, determinism and non-determinism. So which can be recognized by the deterministic pushdown automata, DPDA. Deterministic pushdown automata, and NPDA is nothing but non-deterministic pushdown automata. So here this property which says that, so language which is going to be recognized by the deterministic pushdown automata is called DCFL. And coming to the non-deterministic context free language, which is the language which is going to be recognized by the non-deterministic pushdown automata. So these are the two deterministic properties of the context free languages. And what are the examples of context free languages? So here coming to the parenthesis matching in code. So till now we in the theory of computation we are discussing about the strings starts with, ends with, starts with and ends with. So this kind of languages we are discussing. So in real time where we are going to use this kind of pattern matching, or whether this string which is having the pattern which is going to be accepted or rejected, where we are going to use this examples, this kind of languages we are going to use in the real time, in the sense here in programming. So programming, so parenthesis matching in the code. So if we compile one code, we will get some errors when we are not matching with the braces. How we will know the result? The brace is missing, in the sense we are using this kind of models or missions in the programming compiler. So this compiler, what we will do, will take the input and it will check all the string is belongs to which is going to be generated by the language is accepted by this mission or not, we will check. So like that, here whenever the parenthesis is there, we need to check for the another closing parenthesis. See, if we have this kind of in a print statement, print statement, we have this kind of syntax to write the print statement. If you write something, if this process is missing and we just kept like this, so it has to the mission what whenever we compile the code, we need to get the matching parenthesis, otherwise so the code is going to be wrong and we need to tell them the bracket is missing. So we need to check how we will check this braces matching, in the sense by using the by designing the compilers with this kind of missions. So this is one example. So parenthesis matching in code and syntax checking. So we need to check for the syntax. So these are all the real-time examples of this kind of missions or models. And language of balanced parenthesis. So here language of balanced parenthesis and a program containing if then else statements. So if condition then the statement, else statement, or if condition then statement. So we need to check if the if is there, we need to search for the statement, or if is there, we need to check for the else statement. So these are all the examples of context free languages which we are going to use in the real time. And applications of context free languages and context free grammars. So compilers use parsers for syntax checking. So these are all the examples where we can use. And so in the compiler designing, we are going to check for the syntax. So there we can use this context free languages or context free grammars. And parsers can be expressed as CFG. So here what are the parsers are there, we can express in the way of context free language, context free grammars. So these are all the examples and applications of context free languages. So here what are the coming to the context free language introduction. So it is a generated by the language which is going to be generated by the type 2 grammar and which is accepted by the machine called push down automata. And what are the properties we have for the context free language. So one is a closure property and disclosure properties and deterministic properties. So these are all the properties of context free languages. And context free language examples where we can use in the programming. So in programming, we need to check if we need to check for the parenthesis matching or syntax checking, or if balanced braces statement we need to check, and if then else statements. So these are all the things we need to follow in the design in the compilers. And context free grammars. So till now we discussed about the context free languages and what is meant by context free grammar. So it is a type 2 grammar we discussed. So type 2 grammar. So what are the limitations of type 2 grammars we will discuss. So here whenever we have the different types of grammars. So in this one we already discussed in the previous videos how the grammar is going to be divided. So grammars are divided based on the production rule or based on the ambiguity and unambiguity and different types of non-deterministic or deterministic. So like that we have different types of grammars we can divide. So in this type 2 grammar, based on the production rules, we have the limitation. So left hand side and right hand side we have the production. So here let me write the production. So alpha tends to beta. So here the alpha length is only 1 and beta length it is a combination of V union T. We will see. So what is this V and T? So this is about the limitations of type 2 grammar. So then what is the type 2 grammar and formal definition we will discuss. So it is a formal grammar which is used to generate all possible patterns of strings in a given formal language. So in a given formal language, when we need to recognize the strings, we are going to use this for context free grammar. And what is the definition? So definition, usually the grammar contains, it is a 4 tuple notation. So we represent it is a finite set of non-terminal symbols, and T represent it is a finite set of terminal symbols. So generally T is represented with the lower letters, and V is represented with the capital letters. And coming to the P, so P is nothing but it is a production, so which is in the form of alpha tends to beta. So here the production rule which is used to replacing the non-terminal symbols. So here non-terminal symbols, and it is the string with other terminal or non-terminal symbols. So right hand side of the production, it is a combination of terminal or non-terminal, and also so left hand side which is equal to, we can also use the terminal, single terminal also. And this is about the production P. And S, coming to the S. So S is the start symbol which is used to derive the string. We can derive the string by repeatedly replacing the non-terminal by right hand side of the production until we all non-terminals have been replaced. So here we are using the start symbol. How we are going to use this derivation? So how we are going to use this 4 tuple? We will, if we have the stat symbol and we have the right hand side value, we can replace the values of the right hand side with the terminal symbols until we'll get all the string terminal. So right hand side we'll get all the values are in the terminal values only. So these are all the definition of context free grammar. So it is having the 4 tuple notation. So G represent is the grammar, context free grammar, and it is having the 4 values V, T, S, P. So V is nothing but V is the non-terminal which is represented with the capital letters, and T is a terminal which is going to be represented with the lower letters, and P is the production. So in the production also we have the left hand side only single non-terminal value, and right hand side it is a combination of non-terminal and terminal combination, and S is the start symbol. So here we will discuss how we will convert the given context free language into a context free grammar. So here we have a more number of examples. We will start from the basic and we will end with the complex problems. So here generally this language 1 says that so A power n and B power n. So here A power n and B power n, so a number of A's followed by number of B's. So if you write the language elaborate, so n value is equal to 1. So initially the value is equal to 1, A is there, and B, A power n is equal to A power 1 and B power 1. So we'll get like this. And for the value 2, AA, BB. And for value 3, triple A, triple B. So if you observe the pattern, so we have number of A's followed by number of B's. So how we will write in the grammar, this language we will represent in the grammar in the sense. So grammar is requiring VSTP. So in that one first is the start symbol. So we will represent S So S tends to. So minimum is here AB. So whenever we have the value AB should be there. So we will write this AB first, and so S tends to AB, we need to represent the minimum length, we need to represent. And second one, so number of A's followed by number of B's. So number of A's followed by number of B's, in the sense we can write this A, S, B. So this is the grammar we have written for the A power n and B power n. So let me check. So here if you want to derive this string, so triple A, triple B. So by using this grammar we can derive this string or not, we will check. So yes, so S I have, so S tends to A, S, B. I need to replace, so A, S, B. And if we want one more A, I need to replace this S with A, S, B. And if we want one more A, we need to replace A, S with A, S, B. So finally S tends to or else. So here we already have. So here we already got double A's, and if we replace S with AB, so we will get this string. So what is that string? Triple A followed by triple B. So this is how we will form the grammar from the given languages. Suppose here n is greater than, for the same question, so A power n and B power n greater than or equal to 0 if you take, so L, this is L1 and L2 will take, or else, so for the same question, so first minimum language is equal to, so n is greater than or equal to 0. So n is greater than or equal to 0. So n value, if you take n value is equal to 0, we will get A power 0 and B power 0. So instead this is epsilon. We will write it as a epsilon. And next AB and AA, BB and so on. So for this one, we need to write the same grammar like this. S tends to ASB, and we will write this, instead of AB, we will write epsilon. So for the same thing, for same string, how we will write? So if we are replacing with this A, we have to replace with the again ASB, we will take ASB, and if you write epsilon, we will get the same string. So based on the condition, we will change the grammar also. So this is the one type of language we are going to construct the regular grammar for the given language. And for this kind of example we will discuss. So let me write the language elaboration. A power n. So A power n greater than or equal to 0 here. So here if you take A power n is equal to 0. So A power 0 and B power 2 is there. So why? Because 0 plus 2, we will get only B power 2. So B power 2, in the sense we will write BB. So this is the first string. And if you write n is equal to 1, A, and B plus 1 plus 2 are 3. So it is a B, B, triple B, and so on we will write. So minimum string is here, BB is there. So here whenever we have the value, minimum value, we need to write this like this. So S tends to, first we will write BB. So we will write BB, and then so here number of A's are followed by number of B's. So A is followed by B's. So how we have written A is followed by B? So A, S tends to B. A, S, B. So if you write for the same grammar, if you want to derive one string, so let me derive this string. So S. So S tends to A, S, B, I will take. So to get one more B, so S is equal to BB is there. So if you write BB, we will get the string A, triple B. So here this is how we are going to write the grammar for the given language, and this is one example. And same this kind of example. So first for this example we will write language. So a power 2n. So a power 2n, the minimum value is n is equal to 1. So n is equal to 1. So a power 2, 1 and b power 1. So what is the a, b? And a power 2, 2 in sense 4 and b power 2. So a power 4 a's followed by 2 b's. So this is a odd number and this is the this is the even number and followed by odd number. And right. So n is equal to 2 power 3 and b power n is equal to 3. So here, so not even odd. So it is a number of b's. So even number of a's followed by number of b's. So 2 power 6. So 2 power 6. B power triple B. So and so on. So here, what is the value of minimum length here? So minimum is here double A B. So if you, and here also we have number of A's followed by number of B's here. And here if you take, so here let me write the grammar. S tends to A, S, B, and here minimum is about A, B. And for the same example, if you take n greater than or equal to 0, so what is the value? So here we need to write, so here we need to check for the language, we need to check. So A, so number of minimum is about A, and we need to follow with the B number of B's. So like this, so double A's is followed by single B. So we need to write like this, and minimum is about A, B. And if you write, so if you take n value is greater than or equal to 0, this should be lambda or epsilon. We will take it as a epsilon. So why? Because initially the value is, so if you take n value is equal to 0, so a power 0 and b power 0. So initially it is epsilon. So that we will s tends to, we can get s tends to epsilon also for n greater than or equal to 0. So this is how we are going to generate the grammar for the context-free grammar for the context-free languages. And one more example. So here a power 2n plus 3 b power n. So first we will need to write the language. Then we will get the clarity. So n greater than or equal to 0 and a power, if you take n is equal to 0, a power 2 into 0 plus 3 and b power 0. So what is the minimum value? A power 3 is minimum length here. Then we will get a power 2 plus 3 and b power 1. So a power 2 plus 3 in the sense, we will get the value 5. So number of A's is 5 and B. So here B power 1. So B. So and here one more time, A power 2 into 2 plus 3 and B power 2. So B is equal to from 0 to and so on. We'll get b power 1 and b power 2 like that. And here what is the result? A power 2. So a power 4 plus 3, it is equal to 7 and b power 2. So first minimum string is, we have triple A. So here we need to write here s tends to. So we'll write triple A first. So triple A first, and we already written A power 2n. So here A power 2n, we have A power 2n plus B power n, we have AASB. So AASB, and so AA plus B, and here the minimum length is triple A. So minimum length is triple A. So this is, and A power 5. So A power 5, which is followed by B. So here it is all odd numbers, 3, 5 kind of thing. So but minimum is about A power 3. Minimum length is A power 3. So this is how we are going to generate the grammar for the given language. And coming to the language 4, so here somewhat critical, we are taking the two values, m value and n value, so that we need to concatenate two operations. So two values we need to concatenate. So let me check how we are going to concatenate, and how step by step we will discuss. So here m greater than n. So m greater than n. For this one, first we need to write. So we'll write for the A value, and we'll write for the B. We'll write for the combinedly. So let me write. So S tends to S1. Will take one more. S1 tends to. So A power n and B power n. So if you have A power, both are equal. So both are equal. We'll get the value like A power n and B power n. A S1B, which is, so A S1B, and here m is greater than. So m value is greater than, in the sense the value of A. So A is followed by B, right? So in this one, the value of A is more than B. So that minimum is A1, one value. So we need to write like that, and this is for, so we will write lambda here or epsilon, and we will write the same thing. So if we have the value A tends to, so here A tends to A, capital A, and so this is about the value, m value is greater than n. So to write this one, here we are additionally adding m value n. So n, if you take n value, it's equal to 0. Obviously n after 0 we'll get 1 maximum. So if we'll take m is equal to 1 and n is equal to 0. So in this one, m is equal to 1. So A power 1 and B power 0. In this one, minimum length is A here. So for this one, we have written like this. And for A, capital A, if you take A, so A is always A power m, which is a combination of this one. So A is followed by, minimum is A, and which is followed by capital A. So this is how we have written single, we are dividing the two parts, m value and n value, and we are writing individually, and we will combine together, we will write the grammar. And here S1 we have taken. So here this A's is followed by B's. So here we will write together. Here we are going to concatenate these two production rules. How we will concatenate? So AS1. So why? Because so A power m is the starting. So that I have written A, capital A first, and then it is going to be followed by the S1. So this is about the production rules. And if you observe S, if you take one value, so m is equal to 2 we will take, and n is equal to 1 we will take. So what is the grammar? So A power 2 and B power 1. So A, B. So, and we'll check for this string. So S tends to AS. capital A, S1. So here we require double A. So A tends to, we have, so A tends to, so A, and we'll take only A power, we will take only this part, this one, A, and S1 tends to ASB, AS1B, and S1 tends to epsilon is there, so that epsilon, if you write, so AAB, we will get the string AAB. So this is how we are going to generate the grammar for the given context-free language. So this is one example, and here we have till now we have combinations of A power n and B power n, and here it is not going to be starts with A and it is only not only followed by B kind of thing. So we have given the language called only W, and it is also a choice of A power n and A plus B whole star kind of thing. So A plus B whole star in the sense it is going to be either starts with A or B and ends with A or B, and the number of A's multiple times it going to be repeated and number of B's going to be repeated, and it is a combination of A-B combinations. So like that we have to take one kind of language, and how we are going to construct the context-free grammar we'll see. So here n of A with the W, and W which is a combination of A power n and B power n, and here, so here for this kind of languages we will write the language. So here number of A's is equal to number of B's here, so that so in this one A plus B, I will write the language A plus B whole star. So A plus B whole star, just now we discussed the language epsilon, comma, A, comma, B, comma, A, B or B, A or B, B and A, A, and so on we will write. So here this kind of combinations we require, so that A starts with A is followed by B, or B is followed by A, or else only A value or B value, like that. So here for this, suppose here A followed by B, we need to take A power A, and we can also use B, S, B, and also, so if the value is two combinations, we will write the SS and the value epsilon. So why? Because epsilon is there. So this is how, let me elaborate. In this one we will write the language AABB, and for this string we will check whether the language grammar is going to be accepted. So S, so A tends to ASB, ASA we will take, and so here instead of, so we require only A, so that we will write the value. So we have the value A and B, so that I will write SS, and A tends to ASB, ASA, and this S tends to BSB, and here S tends to epsilon, S tends to epsilon. We will get the value AA, B, B, and so on. So this is the language, and this is the grammar, which the grammar going to be generated, and this grammar going to be accepted for this string. And for one more example, so here W, which is a reverse, so W reverse. So this is one kind of question, and this is one kind of question. So we need to combine these two grammars, we will see. So here double word, which is a reverse word concatenation, we have the value. So this is about the even palindrome. So generally we will write the values like AB even palindrome, so number of length of the string is even. So and ba, so if you take the length of the string is even, so we can say that it is a even palindrome. So even palindrome. And if it is a value like a b b b a, so this is an odd number, so it is a odd palindrome. So we need to combine these two in a single grammar. So how we will see? So for this even palindrome, how to write the language? So how to write the grammar? So this W, which is a combination of A plus B whole star. So if you take the A value or B value, the string the going to be the string which is going to be starts with A or B. So just now we discussed. So S tends to, so let me write S1 S tends to A S A, and if the string is going to be starts with B, B S B. So and here we have the even number. So if we have one more A or B, so it is going to be odd number. So that for even palindrome we will write epsilon. So this is a even palindrome. So why? Because if you keep the value S value as an epsilon only, we will get the even number. Even number of A's or even number of B's we require for the W reverse even palindrome. And we'll take for the odd palindrome S1 and S2 we will write. So here S tends to ASA. What is the difference between even and odd? In the sense we require the value here. This is same, but the value of middle part is one more B is there. So how we will write for the same grammar? So additionally we will write A or B. So here B as B. And if we have it is in the middle, it is having the A value, we need to write like this. And B value we need to write like this. And here they are asking for the union of two grammars. So how we will write? Let me write the same language as a S. So A power S A. So these are the two things common, and this is going to be add in the grammar. V S B and A B and epsilon. So this is the language. This is the grammar which is going to be generated by the context-free language. So whenever they are asking for the even number of even palindrome, even length palindrome or odd length palindrome, we need to observe this. One is only part is for even we have the symbol epsilon, and for odd this terminal value should be there. So this is the point we need to note for the even palindrome and odd palindrome. And one more, context-free languages to context-free grammar, we have the three values. So till now we have seen only A, B, A is followed by B. So here we are adding one more symbol called C, and the number of A's or number of B's which is followed by the C number of C's. So for this kind of languages, how we will write the grammar? So here the value of A power M and B power M is value same. So let me divide this into two things. So here the grammar, here we have S1 we will write. So if you observe in the previous grammar, we have A power N and B power N. So like that here for the same thing we will construct A power N and B power N. So we have ASB, and if the value is 1 greater than 1, so here we need to write the terminal value. And let me check the value of M. So value of M which is greater than 0, so that we will write the AB values. So A is followed by B and AB. So minimum length is AB. And here if you have the value the C here, so for C, so C power N is there. So N greater than or equal to, so here not M comma N, So here m also, m and n values are both. So m greater than or equal to 0 and n greater than or equal to 0. So that here 0 is also included, so that a power 0 and b power 0 we have epsilon, so that we will write it as a epsilon. And individually n less than or greater than or equal to 0 here, so that c power, so s, c I will write it as a c only. So c power n, how we will write the a power n or b power n? So s tends to a capital as, and greater than or equal to 0 in the sense we need to write the epsilon. So that we will write, if we have a power, so if we have a power 0 is tends to a power a is there, epsilon a is tends to a is there. So and here for the c value we will write the small c and capital C, which is followed by capital C and epsilon. And here we need to combine these two things, and we will write it as a S1 tends to, so S tends to A, S and tends to B, and we will write it as a S tends to S1, S. So why? Because this S1 is followed by C. So this is S1 and this is C. So S1 is followed by C, so that we have to write, we need to concatenate these two production rules. So this is about the context-free language. So and how we are going to convert it to a context-free grammar. So these are all the references which we have taken the examples from this. And here let me briefly discuss. So context-free language, it is a context-free language is a type 2 grammar which is going to be generated and which is accepted by the pushdown automata, and it is having the properties called closure properties and disclosure properties and deterministic property. So and what is main examples, coming to the examples which is going to be used in the designing the compilers, and especially in the syntax checking and programming, we need to use in the programming, like balanced checking, balanced parenthesis checking and syntax checking. We can use this kind of models or languages in the process of designing the compilers. And here context-free grammar, which is having the 4 tuple notation. So 4 tuple notation, which is equivalent to the production rules, which is having type 2 grammar, which is having the production rule. There is a production rule different types. So in this one, left hand side only a single length of the left hand side of the value, non-terminal value only there, and right hand side it is a combination of terminal and non-terminal, and also it is a single terminal also, it is acceptable. And these are all the examples how we are going to convert the given language, context-free language, into a context-free grammar. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.